Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to the various parameters related to motion of an object. So in this video we are going to discuss about the graphical analysis of acceleration. Okay, so there are various parameters which are required to study the motion of an object: distance, displacement, speed, velocity, acceleration. In the previous videos we discussed uniform motion in straight line and variable velocity, non-uniform motion. So in this video we are going to discuss about acceleration. So before we discuss acceleration, so here there are certain components that will come into play. Since we are discussing acceleration, okay, acceleration, it is derived from velocity, okay, it is derived from velocity, and velocity is derived from displacement. Okay, all of them are vectors, okay, having both magnitude and direction. Displacement by time gives us velocity. Velocity by time gives acceleration. We have already covered it in the description of motion, that where we discussed the theoretical and mathematical formulas, everything. Now acceleration, if we want to define it in a good way, it is the change in velocity within a given interval of time, and it is expressed as the change in velocity divided by the time taken. Okay, so it means, suppose we are discussing only velocity and time. Suppose an object, it started from a certain point, okay, and we are taking two time instants, okay, let's say time instant 1 and time instant 2. Both of them are the duration, the gap between them is, let's say, 2 seconds, okay, 2 seconds. At time instant 1, the reading of velocity was taken and it was, let's say, 4 meter per second. That was the velocity at time instant 1, v1. And at time instant 2, the reading was taken, it was around 8 meter per second. This is v2. This is the final velocity reading, this is the initial velocity reading. This gap, delta t, which is the final time instant minus the initial time, that is 2 seconds. Acceleration is equal to Vf, this is I, final velocity reading minus initial velocity reading by the gap, the interval Tf minus Ti, which is equal to 8 minus 4 meter per second by, this one is 2 seconds, the gap, okay. So it is 4 meter per second by 2 seconds, which is 2 meter per second square. This is the acceleration here. So here it accelerated 2 meter per second per second. Okay, so every second the velocity of the object increased by 2 meter per second within this interval. In the first second it was 2 meter per second. In the second 1 second, okay, this was the first 1 second, this is the second 1 second, it was 2 meter per second. So it increased first in this, it was 6 meter per second, then finally it reached to 8 meter per second. So this is the final velocity and this is the acceleration, 2 meter per second square. Okay, this. Now, like velocity, acceleration can also be uniform and non-uniform, variable acceleration. So uniform acceleration, if we want to understand this uniform acceleration, suppose the acceleration at different time instants, okay, the different time slots, we take equal time slots, okay, of 2 seconds, equal time slots we take of 2 seconds each, okay, and here the initial velocity was, let's say, 0 meter per second, okay. Here after 2 seconds, the first 2 seconds, it is 4 meter per second, here it is 8 meter per second, here it is 12 meter per second. So in this time interval, let's say it is 0, it is 1, it is 2, it is 3. We have 3 time instants we have taken. The time interval from 0 to 1, in this time slot, the acceleration is a0, a subscript 0, 1. Final velocity is 4 minus initial velocity is 0, 2 seconds, which is 2 meter per second square. The time slot from 1 to 2 in this time interval, same 2 seconds, we are taking equal time intervals. The acceleration is, final is 8, initial at the beginning of instant 1 is 4, 8 minus 4, again interval is same 2 seconds, it is 4 by 2, 2 meter per second square. Similarly from 2 to 3, the acceleration during this is 12 minus 8, this is the final, this is the initial, by 2 seconds, just 2 meter per second square. So you see, the acceleration is constant, it is uniform throughout. And if we take the total average acceleration over the entire duration, that is from 0 start to end, 0 to 3, A03, it will be called as the average acceleration, okay, average acceleration, it will be total final velocity, which is 12 meter per second, minus initial velocity, which is 0, total time is 2 plus 2 plus 2, 2 plus 2 plus 2, which is 12 by 6, it will be again 2 meter per second square. Here in the numerator it is meter per second, here it is seconds. So in all of the cases, so don't get confused, meter per second by second, velocity by time, it will be meter per second squared. Okay, so the average acceleration is also 2 meter per second square. It is always remaining constant. So uniform acceleration is if the velocity of the object increases by equal amounts in equal intervals of time, then it is called as uniform acceleration. So uniform acceleration is if the velocity of the object increases or decreases, when then if it decreases, then it will be called as deceleration, but let's not bring it here, it will keep increases. Okay, velocity of the object increases or changes, let's say changes, okay, changes will be more appropriate, it can increase or decrease, let's keep it changes. If the velocity of the object changes by equal amounts in equal intervals of time, then it is called as uniform acceleration. So here in this example, the velocity of the object increases by 4 meter per second in every 2 seconds. For every 2 seconds, the velocity increases by 4 meter per second. For every 2 seconds, it increases by 4 meter per second. That gives to an acceleration of 2 meter per second square. Let's take another example. Okay. So here again from the start, we'll take equal time slots. Okay. Let's say 2-second time slot. We'll say in the first time slot for 2 seconds. Okay. T01 again 2 seconds. The velocity is 2 meter per second. Then again in the second time slot, that is T12, again 2-second time slot, the velocity is, let's say, 5 meter per second. Then again in the third time slot, again the interval is the same, time interval is the same, 2 3 is again 2 second. The velocity is, let's say, 10 meter per second. So here for the duration 0 to 1, this acceleration is final minus initial. Here starting is 0 meter per second minus 0, the time slot T01, which is 2, which is 1 meter per second square. That is the acceleration. From the interval 1 to 2, acceleration is final, which is 5 meter per second, initial is this 2 meter per second, time duration T12 is again same 2, which is 3 by 2 meter per second square. Again for the time duration from 2 to 3, okay, acceleration is final is 10 meter per second, initial for this is 5, time slot T to 3 is 2 seconds. So it is 5 by 2 meter per second square. So for every phase, for every equal time intervals, in equal time intervals, the velocity is increasing, is changing by unequal amounts. So here it is 1 meter per second square for the phase 0 to 1, that is the acceleration. Here it is 3 by 2 meter per second square. Okay, 5 minus 2 is 3, yes, 3 by 2 meter per second square, and here it is 5 by 2 meter per second square. Okay, so this is non-uniform acceleration. Okay, this is non-uniform acceleration. So non-uniform acceleration, the definition is if the velocity of the object changes, okay, not increases or decreases, let's keep it changes by unequal amounts in equal intervals of time. Always pay attention that it is equal time slots. Okay, we need a reference thing. Okay, when we keep the interval equal, we can say, okay, in this much interval, for every equal interval, whether the parameter is changing by a fixed amount or a different amount. So you have to keep one fixed. Okay, by equal it is changing by unequal amounts in equal time intervals. Okay, this. So this is non-uniform acceleration. Now, this is the total thing. So here, if we want to calculate the total average acceleration from the time slot 0 to 3, from 0 to 3, total average 0 to 3, it will be final minus initial, final velocity minus initial velocity, which is 0, divided by the total time, which is 2 plus 2 plus 2, T01, T0, T12, T23. So it is 10 by 6 meter per second square. It will be, I think, 5 by 3 meter per second square. This is the average acceleration for this. Okay. Now, let us discuss the different cases of acceleration. For constant acceleration, for variable acceleration. Now, when the first case, when the acceleration of the object is 0, okay, when the acceleration of the object is 0, okay, we know acceleration is equal to delta V by delta t. So when it is 0, it means change in velocity is 0. Velocity is not changing, okay, velocity is not changing. So it means velocity is constant, it is constant, the velocity is constant. So if you remember in uniform motion in a straight line, constant velocity, I said here there is no acceleration, zero acceleration, okay, it means it has a constant velocity. So when acceleration is equal to 0, okay, velocity is constant, okay, constant velocity. This is the velocity time plot for the motion of an object with 0 acceleration or constant velocity. Okay. Next thing is when the acceleration is uniform. This is 0 acceleration. This case is 0 acceleration. Next is constant acceleration. When the acceleration is constant. These are all velocity time plots. Velocity in y-axis, time in t-axis, time in x-axis. Okay. So again, here before we discuss this, I have to discuss another thing. Okay. So we have discussed average acceleration here. Another important thing is the instantaneous acceleration. Okay, instantaneous acceleration. For instantaneous acceleration, let's say we take a plot between velocity time graph. I will come to that, okay, the constant acceleration thing. But let's say we take a velocity time plot which looks something like this, okay. It is variable acceleration, it is non-uniform acceleration, okay. Because we have to discuss this concept of instantaneous acceleration, we will come there. So here, if we want to determine the acceleration between any two time instants, let's say we use a different ink, let's say, okay, we take any two time instants, let's say this one, and we take this time instant. Let's say this is t1, this is t2. So we determine the velocity at the respective points. Here it is, let's say v1, here is, let's say it is v2. So this here is the change in velocity in between this time interval, and this is the time gap, okay. This is here v2 minus v1, this is here delta t is t2 minus t1. So here acceleration is basically delta v by delta t, v2 minus v1 by t2 minus t1. Now, like we have discussed in the non-uniform velocity, variable velocity, where we discussed instantaneous velocity. So for that, what we have to do, let's say we shrink this time gap, okay, this gap between 2 points, point 1 and point 2, okay, this is 1 point, this is 1 point, this is the time gap. if we could shrink this time gap, if we could decrease this time gap to a very small amount, okay, to a very small amount, almost equal to 0, almost approaching 0, not 0 but approaching 0, approaching to 0. So we shrink this time interval. Let's say first we bring it here, okay, this one, it will be the new time interval, then we bring it here, this becomes the new time interval, and then finally we bring it very close, okay, we bring it very close here, okay, and then further close. So when we keep on, okay, when we keep on shrinking this time interval, we keep on decreasing it, decreasing it, decreasing it, decreasing it, decreasing it, it approaches a certain point, okay, it approaches a very certain point, and we have to determine the acceleration at that point. So that is called as the instantaneous acceleration. So we take the help of calculus and the concept of limits. So instantaneous acceleration is basically average acceleration, which we take delta v by delta t, but we add another thing, that is limit delta t tends to 0, okay, that is instantaneous acceleration, that is equal to dv by dt. Derivative of v, okay, derivative of v, velocity with respect to t, where velocity is a function of time, okay, here. So this is the expression for instantaneous acceleration using concepts of calculus and limits, concept of limit, where we shrink the time to this. And basically instantaneous acceleration is the slope, okay, the slope of the tangent drawn at that point, okay, the slope of the tangent drawn at that point, okay, anywhere. If we calculate the instantaneous acceleration, it is basically the slope of the tangent drawn at that point. Like this, okay, this. And here also for velocity time plot for acceleration, this here, okay, the velocity time plot, we know acceleration is equal to dv by dt, or we can write it as dv is equal to a dt. Here we have come back to constant acceleration, dv is equal to a dt. As acceleration is constant, we can take it outside, dt 0 to v, 0 to t, it will become v is equal to a t. So here, as we know, acceleration is basically, from the velocity time graph, acceleration is the slope of the velocity versus time graph. This, any 2 points, we say delta v, delta t, this slope gives us the acceleration. Slope is equal to tan theta, which is equal to delta v by delta t, that is equal to acceleration, okay. So same is the case for variable, this is for constant acceleration. For variable acceleration, if we want to determine the acceleration at any 2 points, we simply take those 2 points, okay, we simply take those 2 points, and then, okay, here we take that readings of velocities and time, this is delta v, this is delta t. So acceleration between 2 points 1, 2 is equal to delta v by delta t, which is v2 minus v1 by t2 minus t1. So it is basically the slope of the line joining these 2 points, the slope of the line joining these 2 points, this. Okay, this is delta t, this is delta v, slope of the line joining these 2 points. And now when we decrease this time interval to 0, we decrease this gap, it becomes the instantaneous acceleration at any point, which is basically the slope of the tangent drawn at that point, which gives us the acceleration. The slope of the tangent drawn at that point, which gives us the instantaneous acceleration. Okay, so we have covered constant acceleration, uniform acceleration, variable acceleration. So if we want to analyze, okay, different things related to it, so here let's say we take this case. So here let's say we take this velocity time plots, two different types of velocity time plots, which gives us acceleration. This is one and this is one. So here if we divide this into two parts, okay, here for here and up until this point, this is the first part and this is the second part. So the second part, this is the initial starting from origin. So here if you see, we know that the slope of the plot, the graph, it gives us the acceleration. So here if you see, in this initial portion from 0 to 1, in this region, if you see, if we take any 2 points, okay, these 2 points, let's say, in between these 2 points, this is the time gap, whereas this is the change in velocity. This is the change in velocity. So if you see, the change in velocity is very less as compared to the change in time. Acceleration is equal to delta v by delta t. This is low, this is high, so it means acceleration will be less. But in this phase from 1 to 2, if you see, in between any 2 points, let's say this point and this point, here this is the change in time, okay, this one, this is the change in time, and this is the change in velocity, okay, this is the change in velocity. Here the change in velocity is very high as compared to the change in time. So here the acceleration, here let's say it is from phase 0 to 1, here in the phase from 1 to 2, it will be high because the change in velocity is high as compared to the change in time. Okay, so acceleration will be more. Same is the case for this. Here also if we divide it into two parts, this is one and this phase. In this region, if we take 2 points, okay, here the change in velocity from phase 0 to 1, the change in velocity is very high as compared to the change in time. Okay, in this much time there is a rapid increase in velocity, so acceleration will be more. Okay, acceleration will be more because numerator is increasing, denominator is decreasing, so acceleration will be high in the phase 0 to 1. But in this phase, if we take 2 points, any 2 points, this is the time duration, and this time duration the increase in velocity is only this much. So here the velocity increase is very low in the same time interval. So the acceleration will be very less. Velocity increase is low, time is high, denominator is high as compared to numerator. So here acceleration will be low. So at any point, if you want to extract information related to acceleration from velocity time graph, all you have to do is determine the slope. Here the slope is high, here the slope is low. Okay, here the slope in this phase 1 to 2 is high, from 0 to 1 is low. This is the low phase, this is the high phase. Okay, similarly, okay, this is the low phase, because slope is low, less, this is the high acceleration phase, rapid increase in velocity with respect to time. Here, as you can see, in the initial phase, slope is high, so high acceleration phase. In a small period of time, in a small interval of time, there is a rapid increase in velocity. But in this phase, even though the time interval is high, within that given time, high time interval, the rate of increase of velocity, it is low. So this is a low acceleration phase. Okay, this. So here we have discussed some concepts related to acceleration. Another important thing is that for yes, we know that velocity is derivative of displacement with respect to time. Acceleration is derivative of velocity with respect to time. Okay, this is rate of change of displacement with respect to time, velocity. This is rate of change of velocity with respect to time, acceleration. So we can write acceleration as d by dt of dx by dt, which will be basically double derivative of displacement with respect to time, the second order derivative. Okay, so these are some basic concepts related to acceleration, the graphical analysis of acceleration, where we try to understand the different nature of graphs, velocity time graphs, and how we can extract information related to acceleration from that, about average acceleration, instantaneous acceleration by shrinking the time interval. So here we have discussed that. Okay,